Perfect.
Ciao.
Ciao, Mauro.
Ciao.
I see the people arriving still, but anyway, probably I'll start with the presentation. And good afternoon, everyone. Welcome back to ABM4Policy seminar series. This is going to be the penultimate seminar before the year ends. And probably you will have received the call for the new seminar series starting from February. We would be happy to host you as a presenter in the new year. So if you would like to, please communicate, contact us. So I'm Lilith Popan and I will chair the seminar. Today our guest is Georgios Papadopoulos. He is a research economist at University of Cyprus Economic Research Center. We are touching a very interesting topic today. Georgios' talk focuses on the determination of interest rate rules, and it tries to empirically identify the mechanism that approximates the observed patterns of consumer credit interest rates within a data-driven agent-based model. So thanks, Georgios, for accepting our invitation. The floor is yours. You have approximately 40-45 minutes for presentation and 10-15 minutes for Q&A.
Right.
I would ask our participants, in case of questions, either write them in the chat box or write about the intention so I can pass the word for the question. And thank you and enjoy the seminar.
Well, thank you, Lilith, and actually thanks to all the co-organizers of this beautiful seminar series, which allows us to get together during these challenging times indeed. Thank you also everybody for being virtually here to attend my presentation, which is about, or the narrow focus of it is the lending rate mechanism within a data-driven agent-based model. In fact, there is another broader and underlying motivation behind it. Ever since I encountered the agent-based modeling literature, I was attracted by it, by the intuitive way it models the economy. However, as I was reading more and more studies, trying to understand more and more models, two pervasive questions came into my mind. The first one was why and how in one model choose this behavioral rule over another? And the second question was, okay, why don't these models are able to match historical time series, don't have usually a good fit to the data, to the observed data. In fact, late or in the wake of the financial crisis, two authors actually answered my questions that this is indeed a very challenging task, and choosing the rules, at least at that point, was still done by common sense and guesswork, which, as they pointed out, was only sometimes sufficient to mimic real behavior. Of course, we can discuss about what real behavior means, and there are many great studies that do show very good match of the simulated output from agent-based models to empirical regularities, stylized facts in economics, and distributional properties of the data, and so on. But to the best of my knowledge, very few studies of macro ABMs in particular do exhibit a good fit to the temporal dynamics of historical time series. In fact, the most recent one, these are by chronological order, the most recent one was presented in this seminar series was done by Domenico Delegati and Jacob Grazzini, and was presented in September, if I'm not mistaken. So the broader motivation of my study is to develop a building block, fortunately more will come, of an ABM which is indeed close to the data, and in particular to identify the consumer credit interest rate mechanism. So why study consumer credit? Well, for one, there are some policy concerns about consumer credit's growth in some jurisdictions. This relates to my previous work at the Central Bank of Slovenia. Also, it is less data demanding to model. For example, one of the previous studies that I've shown you by Giannakopoulos and co-authors published in American Economic Review, is about the housing market and uses around 2.2 million observations from households to model the housing market. Also, the Bank of England's agent-based model on the same topic, on the housing market, is very, very data intensive. And so being simple can provide the proof of concept of the suggested approach. So briefly, the main results of the study are that the lending rate mechanism, that is both the rule and the specific parameters, is indeed heterogeneous across countries, which is something to be expected. Another interesting finding is that often a simple borrower risk only mechanism approximates the historical series quite well. And overall, that the model is able to replicate the temporal dynamics of several variables of interest. So how to bring an ABM to the data? Again, well, the broad suggestion would be to test each piece of the model against reality. A more specific one by Bianchi and co-authors and Pasquale, Cirillo, and Mauro Gallegati in 2012 is to use actual data to initialize or calibrate an ABM's free parameters and use microsimulation to validate the model. That is, run the model several times, collect the results and compare them with your preferred goodness of fit measure to the historical time series. If they're close enough, then stop. If not, then continue changing the parameters and so on and so forth. This is actually called descriptive output validation and means that the agent-based model is validated if its artificial output, its simulated version, can sufficiently approximate reality. So the extension of this approach, of this data-driven approach, is to reverse engineer the temporal evolution of the variables of interest. Essentially is a calibration exercise, or someone might call it an estimation exercise since we are using actual data, which aims to identify the rule which minimizes the distance measured by some goodness of fit measure between historical and simulated data. Again, the first step is the previous as before. So use actual data to initialize the model so that to embed the model in the economic environment that we want to simulate. The second one is a bit different. So replace all but one element in the model with their historical evolution. And by element here, I mean both agents and or their behavioral rules. And I will elaborate further in the next slides. Third, calibrate the missing rules. Here, I assume that this element is a rule. Calibrate the missing rules parameters and its functional form. So not only limit ourselves in the free parameters, but also change the functional form of the rule. And finally, the last step is to use microsimulation to validate the model. That is, run the model several times, collect the results, and compare them with the real world data. So this is, as I said, this will be done in the interest rate setting mechanism. And in the ABM literature, I could find 4 broad mechanism groups. So the first group of interest rate setting assumes that it is constant or it is a fixed markup of the central bank's policy rate. A second group assumes the interest rate being an increasing function of borrower's credit risk only. A third one, on the other hand, considers it to be a function of lenders' financial health, again, specifically only of lenders' financial health. And another group combines all the previous elements, the policy rate, a borrower, and the lender-related component. In the empirical literature, there is a bit different classification. So there are a couple of items that there is consensus about. So the policy rate is indeed the basis of bank lending rates, and that there is a positive relationship of the interest rate with borrower's risk. However, there are mixed evidence on the effect of lenders' financial health on interest rate setting. Some studies find a positive link, others a negative link. Some find an insignificant relationship, and yet others do find a time-varying or state-dependent link. And by financial health here, I mean that usually is proxied by the ratio of capital plus reserve to total assets. So briefly, the model that I will present to you has three categories of agents and markets. The first category is those agents and markets which are proxied by historical data. These are the firms, the central bank, and the labor market. Another category is those agents and markets which are modeled explicitly, that is households and the credit market. And finally, there is an agent which is a mix of the two. So some part of it is modeled by historical data, and another part of it is modeled explicitly in detail. So as I said, the first step is to initialize the model using actual data. Here I will focus on the example of one country, of Cyprus. And if I have time at the end, I will show you the results for two other countries that I've calibrated the model on. Here, what we should note is that all data sources are publicly available, and in particular, income is not uniformly distributed among households, but instead follows a gamma distribution which obeys the grand average minimum values, the historical ones, and it has the same inequality, the same dispersion measured by Gini coefficient at the origin of the simulation. So moving to the data-driven part is the part that actually proxies the agents and markets with their historical evolution. On the left-hand side, we can see how firms and the labor market are approximated. That is, by income, the income series, the blue solid line on the left, proxies the income that households or working households would receive if they were employed by firms. And the dashed line shows the unemployment, so proxies the labor market when firms would hire or lay off workers. On the left-hand side of the figure, we can see the bank-related series. The solid blue line is the central bank's policy rate, which is again historical input, and three other bank-related series: the deposits, interest rate, debt service to income ratio, and the banking system's capital adequacy ratio. All these series are injected into the model as raw data, period by period. So this is the data-driven part of the model, and next comes the elaborate description of the agents that are modeled explicitly. So instead of using the usual presentation of equations, I will briefly show you this flow chart. After, this is the household's decision tree. After each household receives its income, as I said, based on the previous evolution that I've shown you, it asks itself this question: is my income and deposit sufficient to pay my financial obligations and consume the minimum amount, which is the subsistence level consumption? If not, then this household can be considered as a financially stressed household, and we move on the red part of the flow chart. So if this household doesn't have a loan, it's fine. It consumes that minimum amount here and saves any excess financial resources. On the other hand, if it does have a loan, obviously it cannot repay it, so it misses that monthly payment and again consumes the minimum amount and saves any excess. If this doesn't hold, so if the household's financial resources are sufficient, so it does, if we move on the green part of the flow chart. So this household first will make its monthly loan payment and sets set its desired consumption. The desired consumption, actually, it's a function, a Modigliani consumption function, which is commonly used by the literature. And it is based on the expected income of a household. Just a brief note that for expectations is used the well-established behavioral model of Anufriev and Holmes, the heuristics switching model. So if, again, another question that this household asks is that is my income and deposit sufficient to meet this consumption, this desired consumption? If so, it does that. If need be, it draws from its deposits and saves the remaining amount. If not, we go on the blue part and goes to the bank to ask for credit. It gets some credit, maybe all, maybe more, maybe less, and consumes all it has. The blue part actually is the bank's decision tree. So when a household goes to the bank first estimates the maximum permissible loan it can give, conditional on two constraints, a debt to income ratio constraint and a debt service to income ratio constraint. Based on these two, whichever is the most binding one at each time step, the bank offers credit to the household. The blue part is the interaction between the bank and the household, the borrower, the potential borrower. So if what the household has asked is more than it was given, it will take that maximum amount on the left-hand side of the flowchart, and the credit parameters are finalized, meaning the volume of credit, the monthly payment, and the interest rate. On the other hand, if the bank offers more, and from an intuitive perspective, we can see that the bank wants to maximize its profit by giving more based on its actually permitted values. So the household, on the other hand, will want to get a higher credit in order to consume more. And how much more? This will stochastically vary based on a uniform distribution between what it has asked and what has been offered. So the interest rate setting is three mechanisms are examined. All three have a common part, which is marked in blue, which is the baseline, the central bank's interest rate, policy rate. The first rule, it's a borrower risk only rule or mechanism, which on top of the central bank's policy rate has a function of the borrower's leverage, measured by debt to income ratio. The second rule is considering the borrower's risk and the positive link with the bank's financial health measured by capital adequacy ratio, and the relationship between interest rate and capital adequacy ratio is modeled via this function, which ensures a positive link. It's a concave function. On the other hand, the final rule is again borrower risk and a negative link with the bank's capital adequacy ratio. So what we've seen is actually that the results depend on these three parameters. So we need to calibrate these three parameters per interest rate setting mechanism, these phi, theta, and tau, and also the maximum debt to income ratio of each borrower. So overall, using this parameter space, there are 42 pairs of the first mechanism, 56 pairs of the second one, and another 42 pairs of the third one. So overall, there are 140 configurations, and our task is to examine each one of them, and it's like a horse race, and see which one best approximates the historical series. So let's move on the first rule and the results. On the left-hand side, we can see the distance measured, the goodness of fit of mean absolute error, sorry. And blue colors denote a better performing configuration, that is for every pair of debt to income ratio and for every value of phi. Blue colors or cold colors denote better performing configurations. And on the right hand side, we can see the goodness of fit measure of correlation, which measures the synchronization between the artificial and historical interest rates. So what we can observe, and let me start with the right part of the figure, is that virtually all pairs exhibit pretty high correlation, ranging between 70% and 95%. So, and this is a pattern which was exhibited for every mechanism and every country. So in this particular case, it seems that this measure is not very, very informative. On the other hand, distance between the simulated and historical interest rate series shows a different picture. Clearly, this part of the plot shows some mechanisms which do perform better than the rest. The circle denotes the best performing pair, the one with the lowest mean absolute error, and the axes show those with statistically equal performance to the best one, measured by a t-test. So from the first mechanism family, we have 1, 2, 3, 4 candidates which perform equally well among them. So the second mechanism is, we can see a similar picture, pretty high correlations. Apart from this first column here, the rest are above 50%, to very, very high correlations. But on the left-hand side, we can clearly see a corridor here of mechanisms, of configurations, sorry, which do perform better than their counterparts, for example, here. And this is actually expected, this upward path of this corridor, because it means that for higher phi, meaning higher contribution from the borrower risk component part, a lower contribution from the capital adequacy ratio part is needed in order to reach a better fit to the data. Again, here, the best pair is this one, noted with a circle, and there are another 4 pairs with statistically equal performance. So 5 candidates from this mechanism family, and we move to the last mechanism, which again shows pretty high correlation. So with all of between the historical and simulated series, but it's not similarly well when we measure goodness of fit by mean absolute error. Here, it's we can see downward moving corridor. Again, it is expected for higher values of phi, a lower contribution from the capital adequacy ratio part is needed in order to reach to a good fit with the data. And as we move slowly to lower values of phi, meaning lower contribution from the borrower's part, a higher contribution of the capital adequacy ratio part is needed to reach to a good fit. Another 5 candidates from this family are showing an equally good performance. So collecting all the results, we can see the 4 The first 4 are from the first family, from the first mechanism. The next 5 are from the second, and the final 5 are from the last mechanism family. All of them show a pretty good, pretty high correlation with the historical series, but not all of them exhibit the same mean absolute error, the same distance. Obviously, this family here, this mechanism shows lower fit, lower performance compared to the rest, and intuitively this one would be the prevailing one, the dominating one, compared to this one, for example, but we can statistically test that. And this is actually the results of the statistical test. So the mechanisms are on both axes, and each point here is a comparison between each mechanism with every other. The squares, the black squares, denote a pair in which the candidate on the x-axis performs better than the candidate on the y-axis. For example, mechanism number 1 performs better than a mechanism number 5, and so on for the rest. The filled triangles show the opposite, that the candidate on the x-axis performs worse, meaning has a higher mean absolute error, a higher distance than the candidate on the y-axis. So mechanism number 10 performs better, than mechanism number 5. And the circles are showing those pairs that show statistically equal performance. Clearly, we can see that in this case, the first 4 candidates, the first 4 pairs, exhibit the best fit compared to any other mechanism. And these come from the simple borrower risk only mechanism family. On the right-hand side, we can see the evolution of these simulated series. And with the blue one is the dominant mechanism candidates, and with gray are from the candidates from the rest mechanisms. Well, here we should note that these goodness of fit measures are estimated over the whole sample period, meaning if we consider the whole sample, this mechanism seems to be performing better than the rest. However, if we focus on smaller parts of the sample, for example, this one here, pre-crisis, for Cyprus it was pre-crisis, we can see that another mechanism could possibly show a better fit compared to the whole sample dominant one. So perhaps there is indeed a time varying behavior on the bank's side. So proceeding to Modulus validation, well, we've seen that on the left-hand side is the evolution of the simulated series of interest rates marked with the blue solid line, and the gray area denotes the range between the 100 runs of the model, the first and third quartile, over running the model 100 times, compared to the historical series, which is the red dashed line. On the right-hand side, we can see the annual growth rate of the series. And in fact, we can see that the fit is not that bad, especially after 2011, after this point here. Similarly, here after 2012, which is a year after, since its annual growth rate, the growth rates are not that different between the simulated and the historical lending rates. Okay, we've calibrated, we found the mechanism that produces these results, but what about other variables? Well, moving to consumer credit, we can see that on the left-hand side, the risk-yield levels also do show quite good fit between the historical series in red and the simulated series in blue. And the same holds on the right-hand side for the annual growth rates of consumer credit. And finally, there is another variable that also shows pretty good fit, which is household consumption. Again, on the left-hand side, we can see the rescaled levels. Here, in this case, after that part, the simulated series show a dip, which is not observed in the historical data. But after that, at least their growth rates, after that part, the growth rates are also exhibiting a very good fit. So this brings me to the conclusions, and so that this study's findings are: the first one is that there is heterogeneity across countries regarding both the mechanism family and its particular parameters. And here I will briefly show you the results for Slovenia and the UK, the other two countries. So on the top part here, we can see the levels of lending rates, consumer credit, and consumption for Slovenia. And the bottom row, the annual growth rates of interest rates, lending, consumer credit interest rates, consumer credit, and consumption. Again, it's quite close. Also note here that a different mechanism family yields those results. And similarly for the UK, the top row, the first column is the lending rate, consumer credit lending rate, consumption, consumer credit growth, consumer credit volume, and consumption. And the bottom row is the annual growth rate of each of the series. Interest rates, consumer credit, and consumption, household consumption. Again, here another mechanism shows these or exhibits these results. It's a simple borrower risk only, but with different parameters. So, as I said, a simple out of the three countries, in 2 out of the 3, it seems that the simple borrower risk only mechanism outperforms the more complicated counterparts for this type of credit and for this period. Possibly a dynamic behavior in banks' interest rate rule, setting rule exists, as we've seen. And overall, the model is indeed able to replicate the temporal dynamics of several variables of interest. Well, being close to the data actually has a potential for policy use. So to provide country-specific scenario conditional simulations or forecasting, for example, as a stress test, and it can provide a quantitative assessment of macroprudential regulations or monetary policy scenarios on interest rates and lending, for example, a maturity limit or a debt service to income ratio limit, cap, or stuff like that. Finally, of course, this is only the beginning, and there are several topics that could emanate from this sort of study. One is the lending rate mechanism stability over time. Another one would be to focus on the bank's liability side, studying the deposits and the associated interest rates. And the grand goal is to gradually replace every input series, which is injected into the model, with endogenous rules and or agents like a housing market, labor market, firms, public sector, government, etc. So thank you all for your attention. And I'm open for questions, comments, suggestions, everything.
Thank you, Georgios, for an interesting presentation. I think it also leaves a lot of room for the future research. And I'm opening the floor for the questions and discussions. Please don't forget to write it in a chat box or write me that you have a question so I give you the word. And thank you, Georgios, for respecting the time. So we have approximately 20 minutes for Q&A, and you're welcome with your questions. I see Mark has a question. Mark, can you unmute you?
Yeah, thanks. Thanks very much. And that was a really, really interesting presentation, especially because I think it's really nice how you compared like the kind of the historical like data with kind of your simulation results. I think like a lot of the papers really don't do that. It's more like a point in time or kind of average, but here you could actually really nice to see how kind of how really like the time series compare, which I thought was really, really nice. So I had a question on kind of your rules. So you had a slide there. Maybe it's worth going back there, especially kind of around how you, yeah, exactly. So how you motivate them. So especially like 2 and 3. So they're, you know, if I just look at the capital adequacy term there, of course they're kind of, you know, opposite cases. So I was wondering, so for me intuitively, you know, I would have said like 2 makes kind of sense because, you know, if you increase your capital requirements, then probably the banks need to pass on that to like the lending rate. Maybe I can come up with a story as well that that would fit with 3. Maybe on the other hand, there's like, you know, a U-shaped relationship or something like that in there. So can you maybe talk a little bit more about kind of what motivates you to pick like these specific forms and kind of, and obviously it will have an effect on your results, but like, you know, just give us a bit more intuition if you can. Thank you.
Well, thank you, Mark, for your question. Actually, well, the first one is the most intuitive one. It's it uses the borrowers, the potential borrowers' leverage, and this is sort of standard in the literature to price the risk. So the risk premium relates to the borrower's risk. Well, on the second one and third one, which do use the lender's financial health. Actually, I wanted to choose 2 functional forms. One which has a positive link because there are with interest rate that is to be increasing with capital adequacy ratio, and there are several theories from the top of my head and from the literature are, for example, for higher equity, bank will charge a higher interest rate because more equity would be at risk. That motivates a positive link with higher capital adequacy ratio between higher capital adequacy ratio and interest rates. On the other hand, there are some theories that do suggest a negative link. So the third rule that is decreasing with capital adequacy ratio. So a more robust, financially healthy lender would want to increase its market share. So it will charge a lower interest rate in order to attract more customers. And that. So the choice of these 2 rules, actually the third rule was also used in some agent-based models, at least the part linking the capital adequacy ratio, this car raised in the minus t. The second one, I could think several functions that could yield similar behavior, that is positive link, a concave positive link with capital adequacy. However, this was the one with only one parameter. So it sort of was simpler or less complex, let's say, because it had fewer parameters to calibrate or to estimate.
Thank you, Georgios. I see Sebastian has a question. Sebastian, can you unmute yourself?
Yeah, thank you. Thank you for the really interesting talk. So my main question is, what is exogenous in your ABM? I think when you start presenting the model, you had 2 figures where you showed the exogenous time series, but I'm not sure if I really understood what is going on. Yeah, this would do. So income, unemployment, and capital adequacy ratio is exogenous. If you could go back to the interest rate setting. So what I wanted when I saw this slide, so in like the second and the third interest rate setting mechanism, but you have the policy rate there and you have the capital adequacy ratio there. So both variables are exogenous.
Mm-hmm. Exactly.
And then you also have, I think it was the debt to income ratio.
No, debt service to income ratio.
Sorry?
It was debt service to income ratio.
Debt service to income, sorry. And then income is also exogenous.
Exactly.
So I don't know how to phrase this question. So a lot of variables are actually exogenous and not determined by the interactions of the ABM.
That is correct. In fact, the intuition is that some parts of the model follow the historical reality of the economy it attempts to model. For example, income, and here it would be better for if I was presenting the growth rate of income. So income is initially distributed unequally among the population, among households, 1,000 households, and then in each time step, period by period, their income grows according to this pattern, or more specifically to the monthly growth rate. Similarly, unemployment. So some household that is employed, if unemployment rises, randomly, a working household will become unemployed and receive an unemployment benefit. If unemployment decreases, a random unemployed household will become employed and receive an income, which from then on will follow the evolution of the historical income series. So the exogenous part here, or the exogenous agent, would be a firm, if we would like to replace these two series, to have firms in the model which would employ households or lay them off and give them the respective income. Similarly, on the right-hand side, for several variables related to the bank. Of course, the central bank is a different agent, and the rest three variables here could be the result of the bank's actions and interactions with other agents. But I abstract from this and instead force them to follow what happened in the reality.
Thank you, Georgios. So we have more time for questions. If you have questions, please step in. If there are no, yep, Sebastian, go ahead.
I ask one more question? This is more out of curiosity. So in many agent-based models, you have a burn-in period in the beginning. Do you have this problem, or yeah, you do?
Yes, actually, a burn-in period was used in order to for the deposits and consumption to reach an equilibrium. So this depends on the consumption functions parameters. So when income equals deposits, and this depends on the parameters, and this in this model, based on the simulations and the parameters, the fixed parameters I used for the propensities to consume, it's around 170 steps periods, and the results are after that period.
Thank you, Georgios. Are there any other questions? If there are no questions, probably I had a couple that are very connected. Okay, I see Mark. Mark?
Sorry, I don't want to take any questions.
Go ahead.
I'm sorry. Maybe it's very, very brief, and then of course, Lila, by all means, go ahead with your questions too. So I was wondering about kind of the methodology, kind of this minimum distance kind of method that you're using. So can you maybe just explain a little bit more exactly how that works? Is it like, for every time step, or is it like in general, yeah, I don't know, it's just maybe a bit more flavor on that. Yeah, thank you.
Yes. Well, actually, it's although I was trying to be brief here and by no means replace what was written in the paper by this presentation, but it's a very simple and intuitive result. Let me go, for example, in this part, or maybe this part here. So the distance actually is measured by the mean absolute error between the simulated, or the average of 100 runs of the model. So I run the model 100 times, collect the results of, in this case, landing rate, take the average, and compare this average, like one would estimate the mean absolute error between the blue series and the red series. So the ones which, and the rest are, as I described, the ones which show the lowest mean absolute error. So over the whole sample period are the ones selected. Their equality is a t-test, a means equality test with unequal variances. So to compare between two series and two rules, and it's a very simple goodness of it measure estimation. One could use different measures like mean squared error, for example, which penalizes more higher errors, larger errors, or any other. But I've also experimented with mean squared errors, and the results are very similar. So it's a very simple and intuitive method, as one would use, for example, in a forecasting model to test the performance of it.
Okay, thanks. Can I just follow up very briefly? Is there a risk, so I'm not sure whether you said like you're comparing the averages. Is there a risk that like things might wash out if, the series is like above and below at some point, or is that, I'm pretty sure if I saw the formula, I would kind of, see it, but like, is there kind of a sense in which, if you do the average and then compare this, there's like potentially some version of the two that look very close, but they're actually not, because they're kind of fluctuating around each other versus like one that's continuously above the other. Sorry if that
all right, I see. Well, I mean, for example, here we could see that these are there is some time dependency, if you may. So the blue lines here and some other candidates do perform well for a lot of time. But for example, here, if one would focus strictly on this period up to here, another rule or another mechanism would show the minimum distance, or a better performance, if you will. However, if one focuses on the whole sample, this result arises. So perhaps there is some time dependency, yes. One would want to break this comparison into smaller and smaller windows to pinpoint in time different periods with different rules. There is, of course, a limitation on the test. For example, how many observations one would use to test the equality of two performances of two means, how many observations one would need. But yeah, that's definitely a topic which merits further investigation.
Okay, thank you.
Thank you, Georgios. Other questions? We had time for the rest of the people to think about the questions. I see none. Probably I proceed with mine. Some of those were asked by Mark. With marvelous coincidence, we had very similar questions, but what I would ask is very connected to both Mark's question and also Sebastian's question. But before, I have a curiosity. So basically, the work is based on non-collateralized loans.
Yes.
So I imagine, at least from my experience, with collateralized loans, those rules wouldn't work. So are there any plans to work with the collateralized loans? And if so, how the rules that you have in mind would work? And my second question would be, could you bit zoom in how the credit is granted to borrowers based on debt service to income and loan to income, and how those fit in and connect with capital ratio? I imagine that probably due to this exogeneity, the link is more loose. And I would like, probably this would make it more evident on, and it would show more clear effect. And probably if you elaborate more, it could be more clear for me. Yes. Those two so far.
Okay.
Thank you.
Okay. Yes, indeed, you are right. This is about uncollateralized loans, which is one of the simplest types of loans one could model. Yeah, indeed, for collateralized credit, definitely one would need, it's not as trivial, one would need to think, for example, even more possibly constraints like, for example, loan to value. What's the value, the collateral of the collateral's value? So perhaps one would want to incorporate that into either the rule itself or into the constraints. For example, here I have only two constraints: debt to income and debt service to income ratio. Indeed, I think, I mean, intuitively, that a more complex machinery, either in terms of mechanism itself or and more constraints would apply. And on top of that, perhaps more data would be needed. For example, if the collateral used was, I don't know, a house, then one would need data about the evolution of the housing market, the values of the housing markets, and so on and so forth. If the collateral used was, I don't know, a car, possibly different data would be needed. So definitely a more complex rule. These rules, I'm pretty sure, would not work as they are now. Different formalization would be needed. So as for the lending rate, sorry, the lending volume. So what the bank does is when a consumer or a potential borrower asks for credit, it knows their income, and based on that income and these two constraints, the debt to income constraint and the debt service to income constraint, it assumes the maximum permissible loan that it can give, both based on debt to income ratio and debt service to income ratio.
Sorry to interrupt. Those maximum ceilings depend on something, on the risk perception of the bank, it's just a fixed ceiling. What is it?
Exactly. I mean, these are exogenously enter into the model, especially debt service to income is, sorry, this red series here, and this dashed red series here. So it exogenously enters into the series. Although that being said, it is based on data, and it is calibrated. Here I have a slide about this debt service to income ratios calibration. So although there are no granular and specific data available, there is a database by the Bank for International Settlements that does have debt service to income ratios for several countries and several sectors. So what I did is to calibrate the trajectory for each scenario that yields the closest results. That is, I have the trajectories from the BIS that is on the left-hand side. So I feed them into the model, take the output, and compare which one of all these and more yields the closest match with the historical series of credit. And then once I find the best candidate, I use it as exogenous into the model. And in fact, here what I've found is that the combination of two yields the best result. So a combination of, because in Cyprus in 2013, so this involves some expert knowledge about the economy. So in Cyprus, the major crisis hit in 2013. So I was, I don't know, suspecting that this part of the series around 2010 and then around 2013 would yield good results. Although, if someone remembers, there was a bail-in in Cyprus and a lot of turbulence in the local economy after 2013. So again, I was expecting that a different declining or a more steep decline would be appropriate. And it turned out that up to this part, this series performed well. And after this period, the other one, this one, performed better. So I made an artificial debt service to income ratio series based on those two, a hybrid one, as I call it, which yields the best fit to not the lending rates, but the consumer credit volumes. And I feed that into the data, and this is the resulting one.
So basically, there is no connection between debt service to income, and how far the bank is from the how much capital buffer it has. Basically, how far is the capital requirement from the minimum requirement? There is no connection between those two.
No explicit connection, although one would assume that given that, for example, the capital adequacy ratio, which is this green dashed dotted line here, it already incorporates every policy, since this is historical data gathered by the SDW, ECB's SDW. So one would assume that any policy interventions, any changes are already incorporated into that. So there is no, it's not so relaxed. It is very, very strict to follow that specific part with all the policies and their effects on it. However, that being said, consumer credit, at least in most jurisdictions and until very recently, was very loosely regulated, and regulators mostly focused on the housing market and left consumer credit less regulated. So I assume that this series, to a great extent, do reflect the bank's risk appetite, if you will.
Thank you. Okay, if there are no questions, we are perfectly on time. Let me thank again Georgios for a very nice presentation, and see you in 2 weeks. Have a great week and get ready for the last seminar of the year. That is going to be in 2 weeks. Thank you and have a nice day.
Thank you, Lily. Thank you all.
Bye-bye.
Thank you. Bye.
Bye.